you for the introduction, and thank you for inviting this fantastic workshop, and thank you for organizing. Today, I'm going to talk about inclusions between quantified probability logics. This talk consists of the following three topics. At first, I will talk about the background of this talk. The second topic is about Artemis lemma, which is the main tool of my work. Finally, I will talk about my results. Okay, let's start the first topic. Let LA be the language of first order arithmetic. In this talk, T, T0, and T1 always denote recursively enumerable theories of arithmetic extending I sigma 1. And let TH of T be the set of all sentences provable in T. And let PRT of X be a natural probability predicate of T. And then it is well known that for any formulas phi and psi, these properties of probability predicate of T hold. The first three conditions are called the derivability conditions. The last one is Leb's theorem, a formalized version of Leb's theorem. These properties of probability predicate can be described using modal logic. The axioms and rules of the modal propositional logic GL are as follows. GL consists, the axioms of GL are A1, A2, and A3. A1 is tautology. A2 is called the distribution action. The third one is the Leb's action, which corresponds to the formalized version of Leb's theorem. The rules of GL are modus ponens and necessitation. So, especially A2 and R2 correspond to derivability conditions. This is the first one, and this is the second one. And A3, as mentioned before, A3 corresponds to Leb's theorem. So to connect arithmetic and modal logic precisely, I introduced the notion of arithmetical interpretation. A mapping F from the set of all propositional variables to the set of sentences of arithmetic is called an arithmetical interpretation. And each arithmetical interpretation F is uniquely extended to a mapping Ft from the set of all propositional modal formulas to the set of sentences of arithmetic inductively as follows. Ft of bottom is 0 equal 1. Ft competes with each propositional connective. And the important clause is the third one. Ft maps the formula box A to the arithmetical sentence PRT of Ft of A. Then we want to know the modal principles which are valid in all under all arithmetical interpretations. So I introduced the notion of probability logic. PL of T is the set of all modal formulas which are provable in T under all arithmetical interpretations. And this set is called the propositional probability logic of T. Then it is easy to show that for any theory means RE extension of I sigma 1. For any theory T, GL is included in the propositional probability logic of T. That is, if a formula A is provable in GL, then for any arithmetical interpretation F, Ft of A is provable in T. And the famous Solovey's arithmetical completeness theorem states that the converse inclusion holds for many theories. That is, Solovey proved that if T is sigma 1 sound, then the propositional probability logic of T is exactly GL. Moreover, Witzer listed all the possibilities for the propositional probability logic of T. I introduced the sequence conTn of pi1 sentences, which is defined as follows. This conT0 is the sentence 0 equals 0, and conTn plus 1 is the sentence conT plus conTn. So this is an iteration of the consistency statements. Then Witzer proved the following two statements. And this is a refinement of Solovey's theorem. First, he proved that the propositional probability logic of T is equal to GL if and only if this theory is consistent. So this theory, the consistency of this theory means T does not prove the negation of conTn for any n. If T is sigma 1 sound, then this set is consistent. So this is the first statement is refinement of Solovey's theorem. Also, he proved that the propositional probability logic of T is equal to GL plus box and bottom. Box and bottom is this formula. If and only if n is the least k, such that T proves the negation of conTk. So he listed all the possibilities for the propositional probability logic of T. And Witzer's theorems, we have that the propositional probability logic of T is a primitive recursive set because GL and this logic is is primitive. The set of all theorems of GL is primitive recursive. So we have this statement. Also, the propositional probability logic of T depends only on the list n such that T proves the negation of conTn, and therefore it depends very little on the theory T itself. And it is easy to show that GL plus box and bottom is a sub-logic of GL plus box and bottom if and only if M is larger than or equal to N. So it follows that the propositional provability logics are linearly ordered. And that is, for any theories T0 and T1, PL of T0 is included in PL of T1, or PL of T1 is included in PL of T0. There are situations of propositional probability logics. By extending the framework of the argument to predicate logic, the probability logic of T may become dependent on the theory T and have more fine-grained properties regarding the probability predicate of T. In fact, many works on quantified probability logic were done, especially in the 1980s. Then I'm going to extend the framework from propositional logic to a quantified modal logic. At first, I would like to explain the language of quantified modal logic. The language of quantified modal logic is the language of first-order predicate logic without function and constant symbols for the sake of simplicity, which is equipped with the unary modal operators, box and diamond. So I assume that the language, the modal logic, and first-order arithmetic have the same variables. Then the notion of arithmetical interpretation can be extended to the quantified modal logic. A mapping F from the set of all atomic formulas of quantified modal logic to the set of formulas of arithmetic satisfying the following two conditions is called an arithmetical interpretation. For each atomic formula P, the F maps P to a formula of arithmetic with the same free variables. And in this case, let's say F maps P of y1 to yn, the formula of arithmetic, formula phi of y1 to yn of arithmetic. So mapping satisfying these two conditions we call an arithmetical interpretation. Also, as in the propositional case, we can uniquely extend each arithmetical interpretation to a mapping Ft from the set of all quantified modal formulas to the set of formulas of arithmetic inductivity, as in the propositional case. Ft of bottom is 0 equal 1. Ft commutes with each propositional connective and quantifier. And Ft maps the formula box A of x1 to xn to the formula of this form. Here, x1 dot and xn dot means that x1 and xn are free variables of this formula. This can be realized by using a primitive recursive term, which primitive recursive term which correspond to a primitive recursive function calculating the numeral of this formula. Also, I extend the notion of probability logic to quantified modal logic. QPL of T is the set of all modal sentences which are provable in T under all arithmetical interpretations. And this set is called the quantified probability logic of T. Then, as in the propositional case, let QGL be, sorry, my telephone is calling, so please wait a moment. Thank you very much. QGL is a natural extension of GL to quantified modal logics. And then it is easy to show that for any theory T, QGL is included in the quantified probability logic of T. Then natural questions arise. Avron asked that, is the quantified probability logic of PA included in QGL? And Boulos asked that, is the quantified probability logic of PA RE? And they are very natural questions, but Vardanyan gave a negative answer to this question. He proved that the quantified probability logic of PA is pi02 complete. So this set, the quantified probability logic of PA cannot be characterized by QGL and any other recursively axiomatized formal system. Also, Montagna proved that QPL of T may heavily depend on the theory T. That is, he proved that if T1 is finitely axiomatizable, T1 does not prove the negation of the consistency of T1, and T0 proves con T1 implies con T0 too, then QPL of T0 is not included in QPL of T1. From this observation, as an example of a consequence of this theorem, we have that for any non-zero natural numbers I and j with j is larger than I, QPL of I sigma 1 is not included in QPL of I sigma j. Please notice that in the proportional case, the PL of I sigma 1 is equals to PL of I sigma j, because they are exactly zero. So the situation are different. Yeah. Moreover, the quantified probability logic of T also depends on sigma 1 formulas defining T. We say that a formula tau is a definition of a theory T if for any natural number n, the standard model of arithmetic satisfies tau of n if and only if n is the Gödel number of some axiom T. So definition of T is a formula defining the set of all Gödel numbers of T in the standard model. A sigma 1 formula defining T is called a sigma 1 definition of T. And then let tau be a sigma 1 definition of T. Then we can construct a sigma 1 probability predicate PR tau of X of T, saying that X is provable in the theory defined by tau. And then for each arithmetical interpretation F, the mapping obtained by extending F by using this probability predicate by constructed by using tau is denoted by F tau instead of Ft. And also I define the quantified probability logic of T with respect to tau as follows. And this is the set of all modal sentences that are provable in T under all arithmetical interpretations. Then Ultima proved that for any sigma 1 sound theory T and sigma 1 definition tau 0 of T, there exists a sigma 1 definition tau 1 of T such that QPL tau 0 of T is not included in QPL tau 1 of T. Please notice that tau 0 and tau 1 define the same theory T. So I think this is somewhat surprising result. And by using the technique of Ultima, I proved this statement. Let I and j be natural numbers with j is larger than I. And there exists a sigma 1 definition tau I of some axiomatization of I sigma I, such that for any sigma 1 definition tau j of I sigma j, QPL tau I of I sigma I is not comparable with QPL tau j of I sigma j. So the situation of the inclusion relation between quantified probability logics is completely different from that of propositional case. From Baldanian theorem, no recursively axiomatizable formal system characterizes QPL tau of T. Furthermore, the inclusion between quantified probability logics seems to be rarely established. From these circumstances, I investigated the inclusion relation between quantified probability logics in order to know more about the dependence of QPL tau of T on T and the probability predicate of T, and to better understand past researches. Okay, let's start the second topic. The main tool of my study is Ultima's lemma, which is used in the proof of Baldanian's theorem. To state Ultima's lemma, I prepare some definitions. We prepare new predicate symbols PZ, PS, PA, PM, PL, and PE, corresponding to the elements of the language of arithmetic. Then for each arithmetical formula phi, let phi star be a logically equivalent arithmetical formula where each atomic formula is one of these forms. For example, the S of 0 equal x, the asterisk of this formula is exists v. There exists v such that v is 0 and S of v is x. And let phi circle be a relational formula obtained from the phi star by replacing each atomic formula with the corresponding relation symbol in this set adequately. So, for example, S0 and the S0 equal x circle exists V. There exists V such that PZ of V and PS of V of Vx. Then this formula is a quantified modal formula, but this is there is no modal operation in this formula, but this is quantified modal formula of degree 0. And let D be the model, this modal formula, which says that for each k in this set, pk and the negation of pk is complete when we read box as the probability. Then we are ready to state Arithmetical lemma, which says that there exists a sentence psi of arithmetic such that I sigma 1 proves psi. And for any arithmetical interpretation F, sigma 1 definition tau of T and area sentence phi, I sigma 1 proves that con tau and f tau d and f tau xi circle implies the equivalence of phi and f tau phi circle. And this is proved by using a version of Tenenbaum's theorem in the models of Peano arithmetic. And originally, this statement is provable. This lemma is proved for PA, but PA can be de Jonge proved that PA can be replaced by I sigma 1. And in the statement of the lemma, the area sentence xi is a conjunction of several basic sentences of arithmetic, such as for all x, there exists y, such that the successor of x is y, and so on. And this is the main tool of my work. And what is important to me is the following consequence of Artemis lemma, which is due to by Visser and de Jonge, which states that for any sigma 1 definition tau of T and sentence phi of arithmetic, T plus con tau proves phi if and only if diamond top and D and xi circle implies phi circle is in QPL tau of T. They proved this proposition by using Artemis lemma. So I give proof of this proposition. Okay. Suppose T plus the theory T plus contour proves phi. By Ultima's lemma, for any arithmetical interpretation of F, I sigma 1 proves this sentence. By the supposition T plus contour proves phi, so we can drop phi, and then we have that T proves contour and F tau of D and F tau of Xi circle implies F tau of phi circle. Then these sentences are images of F tau. So we have that T proves that the T proves F tau of diamond top and D and Xi circle implies phi circle. Since F is arbitrary, this sentence is in the quantified probability logic. On the other hand, for the converse direction, suppose that this sentence is in the quantified probability logic of T. Then let F be an arithmetical interpretation such that for each K in this set, F of PK is the intended arithmetical formula. For example, F of PA of XYZ is X plus Y equal Z, because A stands for the addition, 0, successor, addition, multiplication, and so on. And then it is easy to show that I sigma 1 proves F tau of D, because this formula is delta 0, and D states that, I go back, and D states that PK and the negation of PK are complete. So since intended formulas are delta 0, I sigma 1 proves F tau of D, and I sigma 1 proves F tau of Xi circle, because F tau of Xi circle is equivalent to Xi over I sigma 1. Also, I sigma 1 proves phi is equivalent to F tau of phi circle. Since from the supposition, we have that T proves contour and F tau of D and F tau of Xi circle implies F tau of phi circle. So I sigma 1 proves this sentence and this sentence, and this sentence is equivalent to phi. So we have that T plus contour proves phi. So this completes the proof of the Visser and de Jong's proposition. This result shows that QPL tau of T has the complete information about the set of all theorems of T plus contour. Moreover, the following corollary concerning inclusions between quantified probability logics is important. If this inclusion relation holds, then T0 plus contour 0 is a subtheory of T1 plus contour 1. This is an easy corollary to the proposition. I gave a proof. Suppose this inclusion. Let phi be any array sentence with such that T0 plus contour 0 proves phi. Then by the proposition, we have that this sentence is in the quantified probability logic of T0. From the supposition, this sentence is also in the quantified probability logic of T1. Then also by the proposition, we have that T1 plus con tau 1 proves phi. So this theory is a sub-theory of T1 plus con tau 1. So if T0 plus con tau 0 is not a sub-theory of T1 plus con tau 1, then the inclusion doesn't hold. This let's say something like this. This explains why the inclusion rarely established. Okay, finally, I am going to talk about my results. Inspired by Visser and de Jong's proposition, I investigated further consequences of inclusions between quantified probability logics that result from Artemus' lemma. And I proved this theorem. This is one of my main theorem. Let tau 0 and tau 1 be sigma 1 definitions of T0 and T1 respectively. Suppose the QPL tau 0 of T1 T0 is included in QPL tau 1 of T1. Then the following four statements hold. That first statement says that for any natural number n, T1 proves that con tau 0 n is equivalent to con tau 1 n. The second one says that T0 is sigma 1 conservative over T1. The third one says that for any sentence phi of arithmetic, T1 proves that tau 0 probability of con tau 0 implies phi is equivalent to tau 1 probability of con tau 1 implies phi. And the last statement says that for any pi1 sentence phi, T1 proves that the probability of phi and the tau 1 probability of phi implies tau 0 probability of phi. So if one of these statements does not hold for T0 and T1, then the inclusion does not hold. Also, I proved that when T0 is an extension of PA, then the last two statements can be extended as follows. For any formula phi of x, T1 proves this equivalence. And for any pi1 formula phi, T1 proves this implication. And from the first statement, I obtained that if the inclusion holds, then this inclusion also holds for any n, which says that QPL tau 0 plus con tau 0 n of T0 plus con tau 0 n is included in the quantified probability of logic of this theory. This is the main theorem of the first main theorem of mine. And from this theorem, I obtained several refinements of known results. This is the corollary to my theorem, and which is a refinement of Montaña's theorem. Montaña's theorem is here. I can drop the finite axiomatizability of T1. That is, if T1 does not prove the negation of the con tau 1 and T0 proves con tau 1 implies con tau 0 too, then this inclusion does not hold. This is a proof. Suppose T0 proves this sentence and the inclusion holds. And I would like to conclude T1 proves the negation of con tau 1. From this supposition, then we have T1 proves this sentence by this proposition of Visser and de Jonge. And from my theorem, this inclusion implies T1 proves this equivalence. Then T1 proves con tau 1 implies con tau 1 too. Then by Leb's theorem, T1 proves the negation of con tau 1. So I obtained the refinement of Montaña's theorem. Also, I obtained a refinement of Artemus' theorem. Artemus' theorem is this one, and I proved that I added in the statement of Artemus' theorem, I added the non-inclusion of this one. This is because let tau 0 be any sigma 1 definition of T, and since T is sigma 1 sound, it is known that there exists a sigma 1 definition tau 1 of T such that T cannot prove this implication. And then if the inclusion holds, then the consistency of these two sigma 1 definitions are equivalent over T, but T cannot prove this implication. So I obtained that these two non-implications. This is a refinement of Artemus' theorem. At last, I proved this corollary, which says that suppose that T0 is consistent, T1 is sigma 1 sound, and there exists a sigma 1 definition, sigma 0 of T0, such that T1 proves the local reflection principle, sigma 1 local reflection principle of sigma 0. That is, for any sigma 1 sentence phi, T1 proves a provable of the sigma 0 probability, sorry, how to say, provable sigma 0 of phi implies phi. Then, for any respective sigma 1 definitions, tau 0 and tau 1 of T0 and T1, for any, the QPL tau 0 of T0 is not comparable with QPL tau 1 of T1. From this corollary, I obtained a refinement of my previous result here. I proved that, and this example says that for any non-zero natural numbers I and j with j is larger than I, and for any respective sigma definitions tau I, tau j of I sigma I and I sigma j, the probability, quantified probability logic of I sigma I is not comparable with the quantified probability logic of tau j, I sigma j. So from my theorem, I obtained several refinements of known results. And finally, I also investigated sigma 1 probability logics. Researches on restricted arithmetical interpretations have also been done by many authors. For example, sigma 1 arithmetical interpretation is important. An arithmetical interpretation F is called sigma 1 if for any in the propositional case, for any propositional variable p, f of p is a sigma 1 sentence. Also, in the predicate case, for any atomic formula p of x, f maps p to a sigma 1 formula. Then by restricting our considerations to sigma 1 arithmetical interpretations, we obtain sigma 1 probability logics. That is, for example, the propositional sigma 1 probability logic of T is the set of all modal formulas, propositional modal formulas, which are provable in T under all sigma 1 arithmetical interpretations. And we can define QPL sigma 1 of T and QPL tau sigma 1 of T. Then in the propositional case, the sigma 1 probability logic of T is recursively axiomatizable. In fact, Fischer proved that if T is sigma 1 sound, then the sigma 1 probability logic, the sigma 1 propositional probability logic of T is characterized by a formal system GLV, which is an extension of GL. But in the predicate case, an analog of Bardanian's theorem holds. That is, Beradut proved that the sigma 1 quantified probability logic of PA is also pi02 complete. So the sigma 1 quantified probability logic of PA cannot be characterized by any formal system. However, there is some benefit to deal with sigma 1 arithmetical interpretations in my study. This is because in the proof of Artemus lemma, the sentence con tau and f tau d is used to make the formulas f of pk and the negation of f of pk equivalent to sigma 1 formulas for each k. That is, from this assumption, we have that f tau of pk is equivalent to the probability of the f tau of pk, and the negation of f tau of pk is equivalent to the probability of the negation of f tau of pk. This is why in this statement of Artemus lemma, this sentence is in the assumption. And in the case of a case that f is a sigma 1 arithmetical interpretation, the same result holds without assuming this sentence by adding sufficiently many theorems of Aishikuma-1 to the sentence xi as conjuncts. Okay, I go back to the statement of Artemov's lemma. Here, and xi is a theorem of Aishikuma-1. And so we can add sufficiently many theorems of Aishikuma-1 to xi as a conjunct. Okay. And this is guaranteed by the following equivalences. For example, I forget to write down F, but if PS is a sigma-1 sentence, exists Y, PS is also sigma-1, and the negation of PZ means that X is not 0. X is not 0 is equivalent to the statement that there exists Y, such that the successor of Y is X. And we can find such sigma-1 sentences to other negations. So we can drop in the statement of Artemov's lemma this sentence from the assumption. Then I obtained the following version of Artemov's lemma with respect to sigma-1 arithmetical interpretations, which says that there exists an array sentence xi such that I sigma-1 proves xi, and for any sigma-1 arithmetical interpretation f, sigma-1 definition tau of t, and any arithmetical sentence phi, I sigma-1 proves the sentence which says that f tau of xi circle implies the equivalence of phi and phi circle, f tau of phi circle. So by using this lemma, I proved the second my main theorem. Let tau 0 and tau 1 be sigma-1 definitions of t0 and t1 respectively. Then this inclusion concerning sigma-1 quantified probability logics holds if and only if t0 is a subtheory of t1, and for any formula phi of arithmetic, t1 proves that PR tau 0 of phi is equivalent to PR tau 1 of phi. So I could give sufficient and necessary and sufficient condition for the inclusion for concerning sigma-1 quantified probability logics. As a corollary to this theorem, we have that if the inclusion concerning sigma-1 quantified probability logics, then the inclusion of the usual quantified probability logics hold, because the second condition implies the inclusion of the usual version. I think this gives an order of chaotic world of quantified probability logics.
Some order.
Some, yes. And this is a conclusion of this talk. By investigating several conclusions of the inclusion of quantified probability logics, I showed that the quantified probability logic rarely depends on T and probability predicate, and that the inclusion rarely holds. Also, by providing a necessary and sufficient condition for the inclusion of sigma-1 quantified probability logics, I found some order in the world of quantified probability logics. But this is an open problem. Can we characterize the relation between usual quantified probability logics? That's all. Thank you very much.
Thank you. Thank you for the nice talk.